One NVIDIA GB300 rack can require up to 142 kilowatts. NVIDIA says its future artificial intelligence racks will reach 1 megawatt, starting in 2027. That is more than a 7-fold jump. If a 1 megawatt rack ran continuously for a year, it would use about as much electricity as 840 average U.S. residential customers buy from the grid. And that is only the IT load. It does not include every pump, chiller, battery, or conversion loss around it. So the real question is not whether a faster chip can be built. It is this: what breaks first when one cabinet begins to behave like a small power station? Follow the megawatt and 4 hidden bottlenecks appear: space, heat, grid stability, and money. Start with the rack that exists now. NVIDIA's enterprise reference design says the GB300 NVL72 contains 72 Blackwell Ultra GPUs, 36 NVIDIA Grace processors, 9 NVLink switch trays, and 8 power shelves. The full rack can require up to 142 kilowatts, and it is liquid-cooled. This is not just a stack of independent servers. The 72 GPUs are connected so they can work as one large compute system. That tight connection is valuable because data can move between processors without leaving the rack-scale fabric. But density creates a physical trade. More computing inside one rack means more electrical current, more heat, and less room for the equipment that keeps the processors alive. The rack is becoming a system, not a shelf. Now multiply its power by 7. The first limit is surprisingly simple. There may be nowhere left to put the power supplies. One important distinction: the 1 megawatt figure is a roadmap, not the power drawer of every artificial intelligence rack operating today. NVIDIA says full-scale production of its 800-volt DC architecture is planned to coincide with its Kyber rack-scale systems in 2027. The company describes support for 1 megawatt IT racks and beyond. That matters because the business decision arrives before the hardware. A data center operator planning a new building now must choose transformers, switchgear, busways, cooling loops, backup power, and safety systems that may still be in service when those racks arrive. Build for today's 142 kilowatts, and the building may become obsolete early. Build for a megawatt too soon, and expensive capacity may sit unused. That timing gap is where the technology story turns into a capital allocation problem, and the hardest choice begins with a voltage that sounds almost mundane. Power equals voltage multiplied by current. At 54 volts, delivering 1 megawatt requires roughly 18,500 amps. At 800 volts, the same simple calculation gives 1,250 amps. That is almost 15 times less current. The real system is more complicated than one division problem, but the direction is unavoidable. Low voltage demands enormous conductors. NVIDIA estimates that a 1 megawatt rack using a 54-volt design could require up to 200 kilograms of copper busbar. It also says power shelves could consume as much as 64 rack units at megawatt scale, leaving no room for the compute equipment. Moving to 800 volts DC shifts more conversion outside the compute rack and reduces the number of steps in the power path. NVIDIA claims the architecture can improve end-to-end efficiency by up to 5%. But solving the copper problem reveals the next one. Every watt that reaches the processors eventually becomes heat, and the rack's number is not the building's number. Data centers track overhead with a metric called PUE, or power usage effectiveness. It divides total facility energy by the energy used by IT equipment. A perfect score of 1 would mean every watt goes to computing, which is not realistic. A U.S. Department of Energy guide labels 1.6 as standard, 1.4 as good, and 1.1 as better. Use those values only as an illustration. If the IT equipment averaged 1 megawatt, a PUE of 1.1 would imply about 1.1 megawatts for the facility. At 1.6, the facility would average about 1.6 megawatts. The extra power runs cooling, pumps, fans, batteries, lighting, and electrical distribution. Liquid cooling moves heat away from the chips, but it does not make heat disappear. The heat still has to leave the building, and even a perfectly sized cooling plant cannot solve the next problem. Artificial intelligence loads do not always behave like a smooth, steady factory. Traditional data centers mix many unrelated jobs. Their power changes can partly average each other out. Large artificial intelligence training jobs are different. Thousands of GPUs can enter the same phase together, then leave it together. NVIDIA says that synchronized behavior can create rapid rises and falls in demand, while some generation resources may need from 1 minute to 90 minutes to respond. A rack is no longer only a load. It can become a repeating pulse. NVIDIA's GB300 design tries to smooth that pulse in 3 ways. Power caps slow the ramp up. Energy storage inside the power shelves helps absorb short transients. And at the end of a job, a controlled GPU burn can briefly prevent demand from collapsing all at once. In NVIDIA's reported tests, the combined approach reduced peak demand presented to the grid by up to 30%. That is a company-reported result, not a guarantee for every site. But it reveals a new product category, software and power electronics that make compute look calmer to the grid. 5% can sound like a rounding error. At megawatt scale, it is not. 1 megawatt running continuously for a year equals 8.76 gigawatt hours. 5% of that is 438 megawatt hours. Using the U.S. Energy Information Administration's 2024 average of 865 kilowatt hours per residential customer per month, that saved energy would equal the annual grid purchases of about 42 average customers. This is a scale comparison, not a forecast. It assumes continuous full load, and it uses NVIDIA's claimed efficiency ceiling. The actual result will depend on utilization and facility design, but the arithmetic explains why power conversion is becoming strategic. A small percentage affects transformer capacity, cooling equipment, backup power, operating cost, and how many racks fit behind one grid connection. The chip makes the tokens. Efficiency determines how many tokens the building can afford to produce. This changes the supplier map. NVIDIA's 800-volt effort names semiconductor companies that make power devices, manufacturers that build conversion systems, and data center specialists that integrate the facility. The list includes Delta, Light-On, Eaton, Schneider Electric, and Vertiv, among others. Their roles are different, and appearing on a partner list does not prove who will earn the best returns. But the categories tell us where the bottleneck is moving. First, power semiconductors must switch high voltage efficiently. Second, rectifiers and DC to DC converters must survive around-the-clock operation. Third, switchgear, protection, busways, cooling, and controls must work as one system. Finally, operators need contracts that allocate the risk if a promised megawatt rack arrives late or runs below plan. The money does not stop at the GPU purchase order. It spreads across the infrastructure required to make that GPU usable. So when someone announces a 1 megawatt artificial intelligence rack, ask 4 questions. First, is that number today's measured load a maximum specification or a future roadmap? Second, is it the IT rack alone or the full facility after cooling and power overhead? Third, what voltage architecture carries the power and how much space and copper does it require? Fourth, can the site handle rapid load changes without overbuilding the grid connection? Those questions separate a chip headline from an infrastructure plan. The move from 142 kilowatts to 1 megawatt is not merely a faster computer. It is a redesign of the building around the computer. The chip may set the speed. The power stack decides whether it can run. If you want more technology stories traced all the way to the money behind them, subscribe to Circuit and Ledger.